to e-learning in thermodynamics and fluid dynamics of our bachelor program in renewable energies and environmental technology. In this series, we are going over the phenomenon of cavitation in water and its consequences. What is cavitation? Cavitation is the rapid formation and collapse of vapor bubbles within a liquid. Such cavitation bubbles are formed mainly in locations within the liquid where the static pressure becomes smaller than a liquid's vapor pressure. The phase diagram of water shows if water is in its gaseous, liquid or solid state, depending on temperature and pressure. The horizontal axis of a diagram represents temperature, while its vertical axis shows pressure. The vapor pressure curve is part of a phase diagram. It indicates at which pressures and temperatures water evaporates from liquid to vapor or condenses from vapor to liquid. At a constant pressure of 1 bar absolute, water in its solid state, which is ice, melts to liquid water at a temperature of 0 degrees Celsius. Keeping the pressure constant at 1 bar absolute, liquid water evaporates when the temperature is increased above 100 degrees Celsius. Evaporation of water is not only possible when the temperature is increased at a constant pressure. The other possibility is to keep the temperature constant and reduce the pressure below the vapor pressure. Water can evaporate and condensate at temperatures below 100 degrees Celsius if a static pressure is low enough. This is exactly what happens when cavitation occurs. Bubbles of water vapor form when the pressure in a certain location decreases below the vapor pressure. The vapor condensates back to liquid once the bubble has reached a location with a pressure above the vapor pressure. The low pressure at the exposed edge causes cavitation bubbles to form. At a pressure of 2,300 Pascal, a certain mass of water vapor requires over 50,000 times more volume than in its liquid state. The bubbles collapse as soon as they reach a region with a pressure above the vapor pressure. Because water from the vapor bubble occupies 50,000 times less volume after having condensed to its liquid state, the collapse of each bubble is a spectacular event and emits pressure shocks. Pressure shocks from many collapses result in an audible noise very characteristic to cavitation. The sound used now in the video has been recorded in an experimental setup similar to the one in the animation. But how does it look like when cavitation bubbles are formed and collapse in detail? We can see the formation and the collapse of cavitation bubbles with a diameter of approximately 9 mm in slow motion. In real time, this process takes about 4 milliseconds, and it is a spectacular physical event. Because liquid water occupies many thousand times less volume than vapor, the bubble implodes. It first assumes a ring shape. Shock waves and a strong microjet are the result of a collapse. Let's go through the whole process again. If the local pressure decreases below the vapor pressure, water evaporates. A cavitation bubble is forming, is growing larger, and is transported with the flow to a region with a higher pressure. The bubble stops growing. If a local pressure exceeds the vapor pressure, vapor condenses, starting from the bubble's wall. Its surface starts to break down at its weakest spot. A microjet forms and pierces into the bubble's opposite surface. The bubble is now collapsing. The bubble becomes a torus and disintegrates further. The microjet continues to flow in the liquid and can hit a wall. Through its concentrated impact, even high-strength material can be damaged. The implosion releases energy in a very short time concentrated in a very small spot. If the microjet hits a surface, it damages the material by a localized, short-term overstraining. The material starts to evolve microcracks and later material can break off.
Now pay attention to this because two things are going on. Hydraulic vibration and acoustics, okay? So what is this phenomena, okay? And it's hydraulic shock. It's a momentary increase in pressure in a liquid system due to the sudden change in velocity of a fluid. That's the key point. It's not necessarily stopping the fluid, but a rapid change in velocity, okay?